Okay, let's dive in. We've got some great source material from you, our listener, and today we're tackling something pretty major from, wow, over 20 years ago now.
Yeah, the Halloween space storms of 2003.
Exactly. And it feels like a perfect benchmark,
Mm.
for understanding how things happening way out there impact us right here today.
Absolutely. It's a classic case study, really. Shows how the sun, millions of miles off, can, well, mess with the technology we rely on every single day. Those 2003 storms, definitely a landmark event, really drove that point home.
Right. So our mission today, using this article you sent in, is to unpack what actually happened during those storms.
Mm.
Why were they such a big deal? And maybe most importantly, what did we learn?
Okay, sounds good. Let's set the scene.
Where do we start? The timing, maybe?
Sure. So this all went down late October, stretching into early November 2003. And interestingly, the sun was technically supposed to be calming down.
Calming down. How so?
It was in the declining phase of its usual 11-year cycle. Solar cycle 23 was winding down. But one specific spot on the sun didn't get the memo.
Ah, yes, the article mentions this. NOAA 10486. That was the sunspot region.
That's the one. And it was anything but quiet. Well, hyperactive doesn't quite cover it.
An absolute powerhouse, it sounds like.
Seriously, the source material lays it out over just a couple of weeks. This one region just spat out an incredible amount of energy and particles.
Incredible's right. The article lists, 17 major solar flares from just that one spot in 2 weeks.
17 major ones, yeah. And we're not talking your average flare. These were the big league's X-class flares, the most powerful kind.
Right, X-class. Huge energy releases.
Immense! The source points to a specific one, an X17.2 on October 28th. That's like one of the biggest ever recorded.
Wow.
And it didn't stop there. An X10 flare the very next day, then another big one, an X8.3 on November 2nd. Just boom, boom, boom.
So massive bursts of energy. And the article says these flares often came with something else.
They did, often paired with fast coronal mass ejections, CMEs.
CMEs. Okay, refresh us quickly.
Think of giant bubbles of plasma and magnetic fields erupting from the sun's outer atmosphere, the corona. Billions of tons of solar material hurled outwards.
Okay, huge solar eruptions.
Yeah.
And the key thing for us.
The key thing was that a lot of these massive blasts were pointed directly at Earth.
Earth-directed. That's never good.
Nope. Because when these super fast CMEs slam into our planet's magnetic shield, the magnetosphere, they compress it hard.
Like hitting a shield with a hammer.
Kinda, yeah. And that compression, plus all the high-energy particles arriving from the flares and CMEs, triggers intense geomagnetic storms and radiation storms right around Earth.
Okay, so the sun erupts, the blast heads our way, hits our shield, and then things start to go haywire for our technology.
That's the chain reaction.
And the source material really details the impacts.
Yeah.
Where should we start with the consequences? It seems like a lot happened.
Well, the most direct hits were obviously in space itself. Anything orbiting Earth was basically in the firing line.
Satellites. Makes sense. The article mentions loads of them experiencing issues, anomalies, going into safe mode.
Yep, safe mode is basically hunkering down, shutting off non-essential bits to try and ride out the radiation storm. Standard procedure, but you don't want it happening often.
But sometimes it wasn't enough. The article mentions a specific loss.
Tragically, yes. Japan's ADOS-2 satellite. The timing strongly suggests it was permanently damaged, likely killed by the storm's intensity. A major loss.
Wow. And it wasn't just the high-orbit satellites, right? Even lower ones felt it.
Right, low Earth orbit, LEO. What happened there is interesting. All that solar activity heats up Earth's upper atmosphere,
Okay.
which causes it to expand, puff outwards a bit. So
yeah.
even the very thin atmosphere way up there gets denser.
And that affects LEO satellites.
Yeah, it creates more drag, like trying to run through slightly thicker air. It messes with their trajectories, makes them less stable, harder to predict.
Drag from the atmosphere getting thicker because of a solar storm.
Yeah.
That's wild. What about people in space? ISS crew.
Oh, absolutely a concern. Astronaut safety protocols kicked in. The source says the ISS crew had to implement shielding measures.
Meaning they went to more protected parts of the station.
Exactly. To minimize their radiation dose during the peak activity.
And NASA actually stopped spacewalks. EVAs?
They did. The article confirms NASA delayed planned EVAs. The radiation levels outside the station were just too risky. It directly impacted planned work.
So, major effects in space on hardware and humans, but it didn't stop there, did it? These storms reached down to the ground.
They definitely did. A really significant one was the impact on power grids.
How does that work? Sun stuff affecting power lines.
Through something called geomagnetically induced currents, or GICs. Basically, the big magnetic disturbance from the storm can create unwanted electrical currents flowing through long conductors on the ground.
Like power lines.
Power lines, pipelines, yeah. And these GICs can overload transformers, cause protective relays to trip, basically disrupt the grid.
And the source points to a real-world example.
It does. Northern Europe got hit quite hard, partly because of its geology and latitude. The article specifically details a major power outage in Sweden.
A blackout in Sweden caused by a solar storm. That really brings it home.
It absolutely does. Shows the connection isn't just theoretical.
What else? Communications took a hit, too.
A big hit. High-frequency radio, HF radio, suffered widespread blackouts.
That's important for.
Crucial for airplanes, especially those flying routes over the poles. They rely heavily on HF radio to communicate way out there.
So planes had to reroute. The article mentions that, right?
Yeah, the FAA documented it. Airlines had to divert flights to avoid the communication blackouts and the higher radiation levels over the polar regions during the storm.
Okay, so routing changes, communication loss. What about newer tech, like GPS?
Even GPS wasn't immune. The storms really stirred up the ionosphere, that layer of the atmosphere GPS signals have to travel through.
And that messes with the signals.
Yeah, it can scramble them, weaken them, make navigation less accurate, or even unavailable for periods. So global navigation systems definitely felt the effects too.
Power, aviation, navigation, pretty much all the pillars of modern infrastructure.
Yeah.
But there was one effect that was maybe less disruptive and more spectacular.
Ah, yes. The auroras.
Yeah.
The northern and southern lights.
Which you normally see near the poles.
Exactly. But during these storms, they were seen way further south than usual. The source lists sightings in places like Florida, Texas, across the Mediterranean.
Florida. Seeing the aurora borealis from Florida.
Incredible, isn't it? And also reported down in Japan and Australia, NOAA aurora watch logs apparently went crazy. Seeing them that far from the poles just tells you how massive the geomagnetic disturbance was. The whole magnetic field was ringing like a bell.
Wow. Okay, so massive disruption, but also these incredible sights. From a scientific perspective, though, dealing with all this chaos, what did we actually gain? What did we learn from it?
Well, events like this, as disruptive as they are kind of a goldmine for scientists. They provide a real-world stress test of the whole Sun-Earth system.
A chance to study extreme conditions.
Exactly. A rare opportunity to see how everything connects and responds when pushed to the limit. We gathered invaluable data.
And the article mentioned some specific discoveries came out of it.
It does. One really fascinating finding was the temporary creation of a whole new radiation belt.
A new one? Where?
In a zone between the existing belts called the slot region, which was thought to be relatively empty, suddenly, during the storm, it filled up with high-energy particles.
How did that happen?
Later research, like the paper by Shprits and others mentioned in the source, figured out the complex dynamics involved. It showed we didn't fully understand that region.
Any other key scientific takeaways?
Yeah, they also got great observations of how certain types of plasma waves, ULF and VLF waves in our magnetosphere, were energized by the storm and, in turn, accelerated particles to high energies. Work by Balasis and others, also cited, helped piece that together.
So understanding the fundamental physics better. And what about predicting these things?
That too. These storms were a massive test for our space weather models. You know, the complex computer simulations that try to predict this stuff from the sun all the way to Earth's atmosphere.
Like the space weather modeling framework mentioned.
Exactly. Events like the Halloween storms provide crucial data to see where the models work well and where they need improvement. You need these extreme events to really validate them.
Makes sense. So looking back now, 20 plus years later, what's the real legacy of the 2003 Halloween storms? What changed because of them?
I think the biggest legacy is awareness. They were a really stark, unavoidable demonstration of just how vulnerable our modern society is.
Vulnerable to space weather.
Yeah. Before 2003, it was maybe seen as a niche concern for satellite operators or astronauts. These storms showed, nope, this can affect power grids, airlines, communications, things everyone relies on.
So it pushed space weather forecasting up the agenda.
Absolutely, both nationally and internationally. You saw increased investment, better coordination between agencies, more focus on getting forecasts out there.
And industries learned lessons too.
Definitely. The satellite industry, aviation, they improved their designs, their operational procedures, their contingency plans for dealing with radiation and communication loss. Lessons learned the hard way, maybe, but learned nonetheless.
And more investment in the science side too, presumably. better solar monitoring, refining those models.
For sure. The storms underscored just how vital it is to have good eyes on the sun and sophisticated models to understand what might be coming our way. It boosted that whole field.
Okay, so pulling it all together from the source material, it's clear these Halloween storms weren't just another blip of solar activity. They were a real watershed moment.
Totally. A wake-up call. They vividly showed how deeply solar activity impacts our connected digital world down here on Earth.
Revealed how much we depend on a fairly stable space environment, maybe more than we realized.
An environment that, well, isn't always stable when the sun gets active.
Which brings us to that final thought, drawing only from what we've discussed from the source. It really makes you consider, doesn't it, just how interconnected everything is. Our power, our navigation, our communication, all tied to systems that can be seriously affected by forces from the sun, 93 million miles away. What does that deep dependency really imply for how ready we are for the next big one?